Hello everyone and welcome back to a new video in our Introduction to the Finite Element Method series, in which we're going to be starting chapter 6, which talks about the development of plane stress and strain equations as well as elements. Now in today's video we're going to try to talk about the principles of those things, and we are only going to partially start deriving the CST because, as you will soon see, it's going to be a mathematically intensive endeavor, so I thought that I should split it into two videos just to give the chance for the viewers to try to digest all the information we will be showing today. So with that being said, sit back, relax, and of course enjoy the show. Alright, so I'm relying on you remembering your mechanics of materials or strength of materials courses, in which we have a generalistic element that can have 6 possible stresses on that element. You would have axial or normal stresses in all 3 directions, which are the x, y, and z directions, as well as shear stresses on each one of the 3 planes. If you, for example, apply a stress on this plane, then it's the tau of that plane. Now, given Daryl and Logan's way of explaining axes, you have x in the horizontal, y in the vertical, and z in the horizontal again. This tau would be xz because it's on the xz plane. Now, this is in 3D, but we are talking about 2D elements, so of course I have a 2D stress relationship. I have sigma x, sigma y, and tau xy. Now, plane elements can have 2 states. A state which is called a plane stress state or case, and a state which is called a plane strain case or state. So a plane stress case, as the name suggests, is a state where you have basically stresses and only in the plane and nothing perpendicular to the element. Like sigma z, tau xz, and tau yz are zeros. And I personally like to explain this as being a membrane, for example, that we stretch. If we stretch a membrane, then basically if you have like a piece of rubber like this, a membrane of rubber, and you stretch it in all 4 directions, this would be a plane stress case. Now the strains are a little bit different. They are not only going to be in the plane, they are also going to be perpendicular to the plane. And the reason is because of Poisson's ratio. If you have a rubber membrane and you pull it from all sides, the rubber membrane itself gets thinner. And if you have a membrane that can withstand compression and you compress it on all 4 sides, the membrane would get thicker because of Poisson's ratio. Plane strain case is some sort of confined case. It's a little bit harder to imagine, but the idea being that there are only strains in the plane and no strains perpendicular to it. Now, of course, why is this happening? First of all, the strange thing is that if you have strain in the plane of the element, there should be strain perpendicular to the element, right? Because of Poisson's ratio. Now, what's the assumption here? The assumption here is that the strain perpendicular to the element is small or negligible. And the reason behind this could be either because it's negligible itself or it's because it's confined. Now, stresses here, the teaching assistant wrote, exist in all directions. Now, this is MSc and PhD stuff. The BSc level would say there is only stresses, of course, in the plane and the rest is negligible. But in truth, there are some nuances that need to be just mentioned here. You see, since you are confining the movement perpendicular to the element, this means that there are confinement stresses being developed. Of course, those are not part of our discussion, and this only happens if you actually confine the strain. So it's a really deep topic, and I don't want to go into it. I just want to mention it generally. Now here we need the material matrix. They also call it the stress strain matrix. Of course, the question here is that comes into mind, matrix? I've never seen this before. Like previously we had like epsilon x, I mean it's here, we had sigma x equals E multiplied by epsilon x. There was no matrix involved because it was a 1-by-1 matrix, if I want to call it between 2 parentheses. Because our element was 1-dimensional, you had 1 strain and 1 stress, and the relationship between them is done via 1 constant. Now suddenly you have sigma x, you have sigma y, and you have tau, so you have 3 stresses. And you also have strains, epsilon x, epsilon y, and gamma xy. So now you have 3 strains and 3 stresses. Now I know what you're thinking. You might think that, okay, I don't need this matrix, I can still deal with it in a simple equation like this. Well, if we remember correctly, in a 1-dimensional element, sigma x equals E epsilon x, that's all we needed, and there was not a matrix, or a matrix of 1-by-1. Now since we have multiple sigmas, you need a full-fledged matrix here to connect or basically relate the strains to the stresses. There is a long derivation in the book, but basically you have a plane stress system and a plane strain system, and each one of those gives you the matrix. This matrix D connects sigma x, sigma y, and tau xy with epsilon x, epsilon y, and gamma xy. Now, one thing that might come into your mind is to say, I don't need this matrix. I can just say sigma x equals e epsilon x. I can also say sigma y equals the same thing, e epsilon y. Tau equals g multiplied by gamma. This is not really true. Well, it's because this is an approximation. It works well for a one-dimensional space because I don't have stresses on the perpendicular direction. But truth to be said, epsilon x equals not only sigma x divided by e. I mean, if I want to derive it inversely. No, it equals sigma x divided by e minus sigma y divided by e multiplied by Poisson's ratio. Wondering, how did I get this equation? You see, epsilon x equals the direct effect of sigma x over e minus the secondary effect via Poisson's ratio for epsilon y, which equals sigma y over e. So there is like a 1 minus nu or Poisson's ratio, and this nu Poisson's ratio thing is what you will see in the matrix. You can see there is coupling suddenly. Sigma x doesn't only rely on epsilon x, sigma x relies on both epsilon x as well as epsilon y. Why? Because epsilon x itself is relying on both things. So there is coupling, and the idea of having one e for the x component and one e for the y component and one g for the gamma component doesn't work. So your diagonal matrix is not working here. That's the first point. The second point I want to mention is that if you look in this equation, you don't see any g. Like, I thought that there is shear, right? And I thought that I need the shear modulus g, which is the bulk modulus sometimes called. Now, the reason why there is no g is because there is a famous equation, but I forgot. I think it was g equals e, I think, divided by 2. I forgot what the equation was. 2, 1 minus epsilon plus epsilon, something like that. I forgot the equation, but it exists. This equation relates the elastic modulus with the g modulus. So in order to simplify, you could replace g, which you should have found here, by something related to this. You can see it's somehow being shown here, like there is this 1 plus mu, there is the 2. So you can see it's somehow being played out here, although, I mean, I can show it to you. Let me show it to you. Now, let me take this and put it inside here. If you multiply this inside the matrix, forget about the other terms. Let's look at this term. If you take this external term and multiply this inside the matrix, you would get 1 minus 2v eliminating 1 minus 2v, and you would get e over 1 plus nu over 2. So you see exactly this. So you have replaced the bulk or the shear modulus by the elastic modulus to try to simplify things. This is something that the MSc and PhD students don't like. The MSc and PhD students know that there are nuances when dealing with this specific equation. Not all materials, now, for the generalistic part, they do follow this equation, but not all of them. You have some exotic materials like rubber or something. I think that MSc and PhD students tend to disagree here. So, okay, regardless, now, how do MSc and PhD students deal with this? Well, they use a g modulus. Very simple. You can even see Robot defining g and e and nu. If Robot believes in this, then maybe he could just forgotten about g and just calculate it based on those two things. I don't know. I just want to keep this as small food for thought for you to think about when you read those things. Anyway, let's get into the derivation of the CST equations. Spoiler, we will not be able to do this entirely today. Now, triangles are the smallest pieces you can use to build an area. Even if you have a circle, you can discretize it into a bunch of triangles. Of course, it's not going to be 100% accurate, but you can still discretize a circle into a bunch of triangles and deal with it as triangles. Even a rectangle can be discretized into a bunch of triangles. And let's take a look on this triangle, which the book calls IJM, not K. I mean, I thought IJK, but he's using IJM. So zooming in, you see this triangle. This triangle has 3 nodes, I, J, and M. And each one of those nodes can move into 2 directions. It cannot move perpendicular because plane. And the strange thing, it cannot rotate. And the reason why it cannot rotate is because we are not dealing with shell elements, that's one. Two, we can still achieve a pseudo-rotation of this line if, for example, this moves relative to this. Like if this moves to the right and this moves to the left, you are rotating the line. So you can generate pseudo-rotation by moving nodes relative to each other. This would mean that you would have 6 degrees of freedom. This is the element type selection. Notice we are going back to the principles of finite element because this is a fresh element. I cannot just simplify it and show you previous knowledge. Now we need to select the displacement function. Why are we doing this? We are doing the displacement function selection because I want to know the shape functions n. It's called CST and it stands for a constant strain triangle. What does a constant strain triangle mean? It means that epsilon x for the entire triangle is a number, a constant. Epsilon y for the entire triangle is a number, and gamma for the entire triangle is a number. This is an approximation. It's an approximation because it doesn't take into account the positioning of the force. Imagine I have a force pulling in this direction applied on M. Of course, the region around element M should have more strain than the region away from element M. And I'm trying to draw contour lines here. Now, this is a more logical way of dealing with strains. However, this is something that we will not be dealing with today. We will be dealing with constant strain, meaning if you apply a force here, it produces a strain in x and y and gamma that is equal everywhere, which is an approximation, but it's the simplest of elements we can start with. Is there an element that deals with a change in the strain in the triangle? Yes, and it's called the LST, which stands for the linear strain triangle, something we don't know yet. Anyway, we have a constant strain triangle. So to understand how we're going to choose our displacement function, let me just give you a blast of the past. Previously, when we had bars and trusses and whatnot, this was the displacement function we chose. I haven't elaborated a lot about that. I thought it was still new. We are still new to the course, but now we are battle hardened. So let me talk about this. You see, in the truss members, an assumption that we can use for the simplified truss element where I have 2 nodes, I explained this as being adequate because I have 2 nodes. But I hid from you a fact that the underlying assumption of a truss element is that the strain is constant on the entire length of the truss. A small wink to MSc and PhD level students, you could add a 3rd node here and make a linear varying strain in the truss. With all things being said, we had a constant strain truss element, which means that if you have constant strain, how can you find displacement? You have to integrate. If you integrate this constant strain, it's not a linear, it's constant. You get an equation in x, which corresponds to the equation we had before, a1, a2x, or a0, I forgot. What about 2D now? Well, in 2D, the u displacement is gonna have coordinates for x and y, because you can calculate the movement of this point, displacement, not strain, and the strain of this point, and the displacement of this point, the displacement of this point, and the displacement of this point. The displacement of all those points depend on the position along the local x and the local y. Notice, I'm talking about the displacement, not the strain. The strain is constant. So I have to make an assumption of how to find u of xy and how to find v of xy, because I have a movement in x called u and a movement in y called v. So a good assumption we are using here is a1 plus a2x plus a3y. Similarly for v. Why did we choose this? Now, if you were back in the truss days, I would have told you that we have chosen u and v in such a way that gives you 6 A's, those are the things you need to define, because we have 6 movements, we can use those movements to find the A's. That's back in the truss days. But now, since you're battle hardened, allow me to explain to you further. Those displacement functions are not only selected so that we can find the A's based on the deflections we have here, or displacements we have here. No, they're also chosen because you have a constant strain triangle. In a constant strain triangle, we need to have the partial derivative of each of those equations be constant. Take uxy, for example. If you partial derive it with x, you get a2, which is a constant. If you partial derive it for y, you get a3, which is constant. Similarly here, you get a5 for x and a6 for y. And that's very important because we are dealing with a constant strain triangle. If you had a linear strain triangle, you would need extra nodes here to accommodate the linear nature of those strains. So based on the assumption of those 2 equations, we could rewrite this psi is basically the collection of u and v below each other, and this is rewritten in matrix form. Now, of course, We want to find A1 to A6. How can I find them? Those are 6 unknowns. If I have 6 unknowns, I need to use 6 equations, and I do have them. I want to write A1 to A6 in terms of the displacement at the nodes, which I can do. Notice that the first 3 A's are related to the U displacement, and the second 3 A's are related to the V displacement, so I can solve each one of those alone. The equations UI, UJ, and UM can solve A1, A2, A3. The equations VI, VJ, and VM can solve for A4, A5, and 6. So if we substitute the U's of each individual node with the coordinates in the equation, we get this system of equations, which we can solve to find A1, A2, A3. Now the book goes all kind of haywire mathematics on us here. Basically, this is the system of equations that finds A1, A2, and A3. If you want to find them, you have to basically solve the equation by multiplying by the inverse. Multiplying by the inverse is something that softwares can do, like MATLAB, Mathematica, Octave. Daryl L. Logan's book is somehow trying to aim also to provide students with the ability to hand calculate that stuff. So what he does is he goes full on mathematic haywire on us and basically gives you an equation for x power minus 1, so the inverse of this, that you can solve by hand. I want to remind you, you could have used MATLAB or Mathematica or Octave to just invert this matrix and that's it. But since in the book Daryl L. Logan, he targets students who can hand calculate, he basically gives you a hand calculated equation for x power minus 1. So he gives you this is hand calculated. Of course you have this abomination, which you have to, unfortunately, in our videos find. Maybe in examples I would just use Mathematica or MATLAB instead. But he does it manually, so he gives you each one of those terms, what it means, and you can basically solve those things. There is a meaning for those things, by the way. This is basically delta y of the other nodes. This is delta y, and this is delta y of the other nodes. If you are at M, that's delta y of the other nodes. This is delta x of the other nodes. If you are at I, then delta x of the 2 other nodes. This is kind of odd. Now I want to blurt out a mathematical term here. It's related to the area below the curve of the 2 elements, to the 2 other elements. But that's just me speaking. Of course, you would have those equations, or you would have MATLAB to find your inverse. A is the area, 2A is double the area, and there is a well-known equation that finds the area of any triangle given the coordinates. This is something you study in surveying. So yeah, I would say that we have x power minus 1. So if we have x power minus 1, we can know that A1, A2, A3 is x power minus 1 multiplied by the u's, and A4, A5, A6 is x power minus 1 multiplied by the v's. Now why do I need this? I need this because I want to find the u equation and the v equation. So plugging this all back in, I get this abomination, and there is a 2a missing, for xy, u, and v. And this equation is purely related to the displacements of the 3 nodes. So the only unknown that you have to plug in here is your x coordinate and your y coordinate. This equation gives you the displacement at any point on the triangle if you know the nodal displacements and the position. Now why do we do this? Do we do this to look cool? Well, the answer is no. We have done this because we want to find the shape functions. Remember, u was equal to n1 u1 plus n2 u2. Now you have 3 nodes, so of course u is going to be equal n1 u1 plus n2 u2 plus n3 u3. With a slight technical difference, in the previous videos I think n1 was 1 minus x over L or something for the truss, and n2 was x over L. Those n's were equations in x only because you had a bar element. Now having an area element, those n's will become equations of x and y. You can basically find it here. This is an equation for n1 of x and y. That's n2 of x and y, n3 of x and y, n4 of x and y, n5 of x and y, and 6 of x and y. Spoiler, for the future, I might need to derive n1 and n2, partial derivative to x and partial derivative to y. But that's something we don't know yet. Now, to understand what those n's are, which are basically those ones, those are the mixing functions or the shape functions. They have many names. Interpolation functions, shape functions, weighing functions sometimes. I like to call them mixing functions. I've talked about this before. For example here, say I want to know the displacement of a point near node 1. Like this is node 1, and I want to find a displacement of the point here, this point, which is near to node 1. I would not say it's the average of all displacements because this point is near node 1. So node 1 should have more weight in deciding what the displacement of u is at this point. If the point was here near node 3, then node 3 would have the say. Of course, if the point is in the centroid of the triangle, then the ways would be 1/3, 1/3, 1/3 for each one of those nodes. So to understand this, say we're talking about this point now. Well, this point would give you a shape function for the first node that is 90%, which means node 1 affects hugely the displacement of the point near it. The second would give you, for example, 3%, and the third would give you 7%. Note, just by looking at those values, that it seems that, well, node 3 is closer to the point than node 2 because it has a higher weighing function. But that's something that is not really necessary to understand. Those are the shape functions, and I will repeat it next time, and those are the displacements given by the shape function. So basically, with that being said, we understand now that shape functions are basically mixing and trying to find the displacement of a certain point within the triangle given its coordinate based on the displacements of the triangle at its 3 nodes. Because of the similar nature of the triangle in both directions x and y, you can notice that this is a carbon copy of this, the shape function. And this shape function is a carbon copy of this shape function, and so on. This is a running theme you will find in most of the plane elements, and the reason behind this is really deep, and I want to give a quick idea of why. We have used this as our displacement function, and you can see that there is a similar nature between x and y. X is power 1, y is power 1. There are no nonlinear terms so far. So due to similar nature, you get similar new shape functions here. And that's a running theme you will find in most of the plane elements. And look at this, because they have the same shape functions, you can basically find the psi, which is, what's psi? Psi is u and v below each other. You can rewrite the entire equation by this. Ni, 0, and j, 0, and m, 0. The reasons of those zeros are purely mathematical. The sorting of the degrees of freedom are x and y for node 1, x and y for node 2, x and y for node 3. So when you talk about x, the first component gets a shape function because it's related. The second component doesn't get it because the deflection at u is not related to the deflection at v, and so on. So yeah, that's everything I wanted to talk about today. I want to stop here because I don't want to overload you with a lot of mathematics here. I will continue the derivation of the stiffness matrix in the next video. I want to give a huge constant strain triangle sized shout out to our dear channel members in the contributor level, whose names are going to be shown on the screen, as well as our channel members in the helper level. I want to thank them from the bottom of my heart, as the support of the channel is priceless to me and enables me to continue pushing those videos in time and in the quality I try to achieve. With that being said, I hope that you enjoyed the video and that you find it beneficial. Of course, if you have enjoyed it, then please like as a sacrifice to the algorithm. Comment, share, and subscribe, especially subscribing because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel, and we'll catch you in the next video. Bye-bye.